Hi, my name is Barbara Rama, and these are my team members.
I'm Rania Strom.
And I'm Lainey Reed.
And our fourth team member, Pablo, unfortunately could not be with us today to present. But we are the Stacked Rapid Sand Filtration Theory team, and our team is working on continuing the research on developing a mathematical model to explain physics of filtration. So sand filtration is a very important component of an aqua plant. It's it's actually the last stage in a water treatment plant, and previous teams have worked with varying the different parameters to increase efficiency of the StaRS filters, such as coagulant dosage, changing the influent turbidity, and this semester we'll be focusing on varying the different sand grain sizes and seeing how that could potentially affect filter efficiency. So here's a short timeline of what we did this semester. So beginning when we all came together and we introduced ourselves, and we spent a lot of time going over literature review and also working with head loss calculations to see the head loss in our filters and writing the first report. And in March is a lot of connecting of pipes and waterproofing the apparatus and building a new flocculator. And also that's where we wrote the second draft of our report. And in April, we dealt with a lot of troubleshooting. There were many leaks. We moved sand into our filters finally, and we also fixed the influent clay and coagulant dosages for our system. And in May, we hope to finally run experiments and write our final report.
Alright, so some technical terms that are important for understanding how filtration works. I'm going to go ahead and define them. So active zone is the area where filtration is actually happening. It's the pores that are getting filled with flocks in the filter. So it moves throughout the column, and when the active zone reaches the end of the filter, when all of the pores have been clogged, that's when we reach our failure time. So backwash is the state that happens after filtration and after the filter has failed. So water runs backwards through the system and it fluidizes the sand beds. And so then after that, so then that forces all of the material that was into the pores up and out of the system. So that's very energy consuming, so to minimize the amount of times we have to backwash. Ripening time is the time at the very beginning of filtration that happens when the filter, like the effluent turbidity, is really high, and after less than an hour, it goes down to the maximum effluent, or the minimum, I guess, effluent turbidity. And so then failure time is the time in which the filter fails, which the active zone reaches the bottom of the sand bed. So we want to maximize failure time so that we can backwash the least amount of times. So filtration within a stacked rapid sand filter happens as the particles move down between the sand grains and the active zone. So they start to stick in these pores and they form these little constrictions. And so this constriction is in the shape of a washer, and what happens is the shear force in this washer shape gets really great. It's so great that flocks can't stick anymore within that pore. So that's when the active zone moves down. And so then it continues to move down throughout the filter, and eventually failure is reached.
So connecting what Lainey just said to what StaRS is working towards, past STAR teams have been working to connect filter failure time with different parameters such as flock size or dosage. The ones shown in the picture here is actually dosage. And what failure time is in this figure is when the turbidity slope increases very rapidly, and you can see that in the red box here. Specifically, our current team, however, is working on the parameter of sand grain size. So these are the 3 sand grain sizes that we're using. From left to right is smallest to largest. And in relation to filter failure time, the bigger sand grain sizes are going to have less pores in between them than the smaller ones at the same volume, because they just take up more space as bigger sand grains, and because there's less pores, there's going to be less active sites, as Lainey mentioned previously. So therefore, we believe that smaller sand grain sizes with more active sites will cause the flow to move through more slowly because there's more active sites, and therefore increase failure time.
So here's a schematic of our experimental apparatus. So going through it, as you can see in the red box, is our the water inlet is where our stream of water is coming in from, and then the flow accumulator is there because it controls like the oscillation that comes from the pump and make sure that we have like a smooth flow of water in our system. And the clay water solution is a pre-calculated ratio between clay and humic acid in order to mimic the makeup of the water that's coming into a water treatment plant. And the influent turbidimeter is controlled through ProCoDa to make sure our influent turbidity is around 5 NTU, just so it can model also like the water that's coming into a filter at the time. And the packed solution is also pre-calculated coagulant concentration coming into our system. And in the contact chamber is where the clay and the coagulant meet for the first time and flocks start to form. And then that process is exacerbated through the flocculator to create more flocks for our system. And this is a setup the beginning of this setup is the same within previous teams, and the next part where a lot of it has changed. But one of the big things we did in this semester is changing the number of pumps we have in our system. The team of fall 2018 put 2 pumps at the time, and after we were looking through our system and remodeling, we decided that it was redundant to have 2 of the pumps, and we only needed 1 pump per backwash, and that has been changed as can be seen in our presentation right now.
So this is actually the current schematic. We made one more change halfway through the semester where we removed the backwash line. So now the backwash line is right at the water inlet, as the air is pointing to. So the water for backwash, and it goes immediately into that. So then in order to make sure that water only enters that line during backwash, we added a solenoid valve there. And then we added a second new solenoid valve at the side of the filters or between the inlet and the filters to make sure that water through backwash is only going through the 3 filters and up through the exit and is not entering the flocculator or the contact chamber. So this is actually a picture of our design. It's exactly the same as the apparatus. The only difference would be if you look at number 2, the clay water solution is over to the side, not because our desk was very crowded. And so one of the major tasks we did was we had to write new ProCoDa. So the previous apparatus had 2 turbidimeters. Had one for inlet and one for effluent because there was one filter column. So now we have 4 total, 1 for the inlet and then 3 for the effluent. So if you look at the red box, that's our new variables that we created for all of the turbidimeters. So then we had to also change some of the methods. All of the methods are the same, we just changed the variables that went into them because, again, we changed the solenoid valves and we changed the turbidimeters.
So as a result of optimizing our solution, we ran into quite a few problems along the way. One of the biggest being leaks in both the system and the pipes for the filters. And so we actually had to replace one of our filter columns with a new one, which took some time. Also, in all 3 of the filters, the sand bed was not fluidizing properly, and therefore we removed a reducer on the pump in order to get an increased backwash rate, and now it's fluidizing as it should be. Also, while we were running, sand began to exit the filter columns into the system because we didn't actually have mesh in one of our inlet pipes. So we had to send these inlet pipes to the lab to get mesh on the inside, and while we were doing this whole process, we generated more leaks. So we had to fix that as well. Also, because of not an ideal transfer of information between StaRS filter groups. We were unsure of many things, including the proper concentration of Packle and clay stock and how to calculate those. But after consulting other team members, we found MathCAD files that showed the exact formula to go through. So we replaced our stock solution for that and got a new one from those files. We ran some preliminary experiments while one of the turbidimeters was broken, as well as we hadn't cleaned the turbidimeter cuvettes. So after replacing those two things and changing that, we can run new experiments, but that previous data is not exactly usable. We also had trouble with the clay stock leaking, so we've ordered new micro tubing to replace what was there previously to prevent that.
So moving on to future tasks for StaRS team, we hope to run experiments to test the efficiency of each of our filters, and as we're doing that, we also hope to look at different parameters such as varying coagulant dosage in our influence stream. And another big task we have is transferring the MathCAD method to Python so we can have a better transfer of data for the next team to look at this. And we want to do, hopefully, for future teams, want to see an extensive data analysis for three different filters and looking at the different sound grain sizes to determine if it actually does have a great effect to filter efficiency. But thank you for listening to StaRS team, and have a great day.